In this example, we're given several functions defined symbolically. That is, we have an equation, a formula for them, and we're asked to find the domain of each one of the functions and state the domain in interval and set notation. So this first example, we've got f of x equal to 3x plus 2. Hopefully you all look at that and say, I know it's a line, right? It's in that form y equals mx plus b. There are no variables in a denominator. There is no variable under an even root of any kind. So based on what I know about domain, I can say the domain is all real numbers. You can also think about that graphically, right? If you were to graph a line, it will extend infinitely in either direction. Any x we put into that function will have a real number output for y. So I'm going to say in interval notation, we would define all real numbers as the interval from negative infinity to infinity. Notice I'm using open brackets at both negative infinity and infinity because you can't actually get there, right? So we can never include infinity. In set builder notation, I've seen this several different ways, but you can just say the set of all x such that, use that such that bar, negative infinity is less than x is less than infinity. Now, with this next example of g of x equal to x over x plus 1. So right off the bat, I'm looking at that denominator. I'm like, oh, there's a variable in the denominator. That's going to be problematic, right? Because if there's a value of x that makes the denominator 0, that cannot be part of the domain. So what you want to do in this case is take the denominator and set it equal to 0. And then solve that. So we have x plus 1 equals 0, and then subtract 1 from both sides. So x plus 1 minus 1 equal to 0 minus 1. So we have x equal negative 1. So negative 1, and visually we see that, right? If you just sort of mentally put negative 1 back into the equation for x, the denominator is going to be negative 1 plus 1, right? Which would be 0. So what we want to say, and to be honest, when you're just eliminating one value off of the number line, I think it's better to write it in set notation. So I'm going to do that first. The set of all x such that x cannot be negative 1 is how you want to write that. So set of all x such that x not equal to negative 1. Now in interval notation, you're including every single value on the number line except for negative 1. So this is how we're going to do that. It has to be split into two intervals, negative infinity up to negative 1 with an open bracket because you're not including it, in union with negative 1 with an open bracket to positive infinity. Okay? So that those two intervals together include everything on the number line except for negative 1. Okay. I encourage you to go to a graphing utility. I won't do it here, but take a look at what's going on there. You'll find that the graph is tending toward a vertical line at x equal negative 1, but it's never going to quite get there, right? And we call it a vertical asymptote. So we'll get there later, but right now concentrate on the algebra. So in this next example, we have h of x equal to x over x squared minus 16. All right, so same deal as the one we just did, right? We've got that x in the denominator. Doesn't matter what's going on in the numerator. When we're being asked about domain, we just want to know what makes the denominator 0, right? If we have a rational function like this. So I'm going to set x squared minus 16 equal to 0, and I'm going to solve that. There are a couple of ways to solve that. There's no middle term with this quadratic, so you could add 16 to both sides and take the square root of both sides. That would get you there. You can also factor this, right, because it's the difference of squares. So we would have x plus 4 times x minus 4. I'm going to go the factoring route since I want to make sure that we review that. So that would mean that x plus 4 would equal 0, or x minus 4 equals 0. Okay, and then we would have to subtract 4 with this one, right? So we'd have x plus 4 minus 4 equal to 0 minus 4. So x is equal to negative 4. And then with x minus 4 equals 0, we have to add 4 to both sides. So x minus 4 plus 4 equal to 0 plus 4, and x is equal to 4. Okay, so because we're talking about domain, there are two values, right? Both -4 and +4, because we're squaring that in the denominator. Both of those values will make the denominator 0. So again, if you're stating this in set notation, it's acceptable to just say the set of all x such that x is not equal to ±4, right? In set brackets, okay? Now, in interval notation, you're excluding two values, right? So on the number line, you'd have -infinity up to -4, open bracket, right? In union with -4 to +4, open bracket, in union with 4 to positive infinity. So essentially, you've got the whole number line shaded here except for values at -4 and 4, okay? Let's look at j of x equal to the square root of 2 minus x, okay? Now, this is a different scenario, right? We don't have a variable in the denominator in this case. We have a variable under an even root, in this case a square root. So that, remember, the deal is there, if you take an even root of a negative number, it's not a real number. It doesn't have a real number output. So in this case, we have to take the radicand, the stuff under the radical, and set it greater than or equal to 0, because the domain includes values of x that make the radicand greater than or equal to 0. So when we solve this inequality, that will be the domain that we end up with. Okay, so the first thing I want to do is subtract 2 from both sides. So I have 2 minus x greater than or equal to 0 minus 2. Negative x is greater than or equal to -2. And then I want to divide both sides by -1, or multiply both sides by -1. Now remember, with an inequality, when you do that, when you multiply or divide by a negative number, you have to reverse the sign of the inequality. So we'll have x less than or equal to 2. All right, so in interval notation, x less than or equal to 2, we'll have -infinity up to 2, and we're including that, right? Less than or equal to. Also, in set builder notation, we would have the set of all x such that x is less than or equal to 2, like so. Also, with this example, any of these, I encourage you, when you find a domain, to compare what you got algebraically to the graph. What does it look like graphically? You should only see the graph existing for values of x less than or equal to 2.